the curve just by geometry, you have to look more enthused than that.
I'm lost.
No?
No.
Yes, I am.
Okay.
Jonathan,
No, I'm changing. Okay.
we're doomed.
If I'm lost, no. Okay, let's see.
Oh my god, guys.
Should we do minutes before or after?
We're all
Let's
lost.
see if this makes sense. Okay, let's go through it again. Tony's gonna look like he's awake.
Tony is awake.
Okay. We do introduction. What's the introduction?
What are you doing?
The introduction is we're gonna do integrals. We want to find the area under curve, and you're gonna tell me something interesting about the area under curve, and you're gonna find something. We gotta find the. You're gonna introduce the topic, and we're gonna find the area under the curve and find something meaningful with it. All right? Does that make sense? Okay. So the question is, how do we find the area under the curve? We find the area under the curve using Riemann sums. If we take the limit, if I take the limit, I can get an exact Riemann sum. Right, it's going to be exact answer. And then I come back, let's put the order of this. This is 1, this is 2, make sure we're in the right place. 3, this is 4, 5, 6. So that's why I'm doing this, to see how you, when you write it, it has to have a nice flow. A lot of people in the past, if they're not really writers, they write stuff, I don't feel they actually see how it's related. So we have Riemann sums, we have the limit. This means it's going to be exact, correct?
What's 6? There is, it's just blank.
Oh, is that 5? Okay, sorry. Okay, so we did 4 was, we're showing that,
Area under the curve is similar to the, is the same as.
we said the area under the curve is the displacement.
Of the derivative.
And so we're going to make that statement. We're just going to make the statement. I'm going to proclaim that the area under this function is going to be the displacement of anterior, and the way I'm going to justify that is by looking at a simple geometric problem, right? Got it? Are you with me?
Yeah.
So you're not writing. This is not going to. These two things would be all connected. You're not going to write a ton on this. You're going to introduce that, and then you're going to show the example. And then you come over here and you go, and you can also find the area under a curve by using simple geometry like this. But then comes the question, how do you find the area under curve of a more complicated function? Okay, and now we're going to do, now we finally got to FTC2. You agree with me?
Yeah.
I think that makes sense. So this is all, we're talking about stuff, we have Riemann, we're talking about theory, we use a simple analogy. But then you come to how do you actually, and this is where you would actually
Do
the proof. This is the proof of FTC2 essentially. You're going to state that, how do we actually,
You can't call it, but you can't. Nope.
well yes and no. But now we're actually going to do FTC2. I'm not sure that was true. Let's see if I think of that.
You talk to Jerry. Not much.
Alright, so that's the whole build-up, and what did we do? What we did yesterday is what's going to go here, right? Okay, you're actually going to show that you can take the antiderivative. The question is, how do I know in any function, not just a geometric function, how do I know in any function I can take the antiderivative and take the displacement that will equal the area under the function, or vice versa? Do we agree? Okay, so that's what we did. So that's everything we did before. That was a build-up. You have it in your notes, and try to make it flow like it makes sense. Okay, and you could have said FTC2 back there, but this is really the main. We were just messing around today. All right, so this is what we did yesterday, and then when you're done with this, you do FTC1, which is simple. What's FTC1?
Take the derivative of an integral.
All right, it's the derivative of an integral. So if you have an integral of t squared dt from 0 to 2x, and I take the derivative of that. Now, what does that mean?
It's going to be 4x squared.
Now, what is, when we did this yesterday, what is the derivative of an integral?
You plug it in.
What is the derivative of an integral?
How fast the rate of
Right.
change.
An integral is area, and you're taking the derivative area, so you're getting the rate of change.
D area dt.
The rate of change of your area. Okay, so a derivative is always a rate of change, but usually if you're doing a rate of change of a position, this is a rate of change of area. Okay? Now, are you going to show why this makes some sense? Are you going to do the antiderivative, plug it in, take the derivative? First of all, what is our solution to this, the shortcut? What's the solution for
4x squared times 2.
So you plug this in here, right? And so you get 4x squared, and you multiply by what? By chain.
The derivative of the
Yeah, so by chain. Okay, now, what about the case if I put, if I went from, just put from x to 2x?
Then you have to subtract off.
So you basically do it twice and subtract. You bring it in, chain rule, bring it in, chain rule, and then subtract. You remember doing that?
But
Okay.
if it's only one.
So you should show the simple case and you should show the harder case, something like that.
Well, if it's only one, the variable has to be in the upper limit, right?
If there's only one, what's that again?
If there's only one variable, the variable has to be upper one.
If it's just like from a constant to.
Right. Yes. In that case, you ignore the constant. Right. In this case, now, I highly recommend. I'd like you to do both cases where you take the antiderivative and then take the derivative and show that it actually works. You got it? You with me? So when you're doing this problem, you would actually take the real antiderivative, plug in the values, take the derivative, and show that it actually comes out to be the exact same answer, right? And then try it with this one too. Okay? You could use the exact same one for all I care about. I don't really care. You don't have to use a difficult problem, just one so you can see it. I know, thank you. That was good. That was actually very good. And by the way, the reason they have two different variables, because this is like if you graphed it, you're going from two different locations, and x and 2x. So you're using x and 2x as your location. This is the variable of the function. So there are two different variables. It's confusing, but that's what it's all about. You just took a picture off your. What is that? Is it an iPad or what? Oh, it's a cheater? It's an imposter?
iPad.
It's a tablet.
It's better than an iPad.
Oh, you don't say
How's
words
the
like
camera?
that. You don't say words like that in this
The
class.
5 megapixel.
Whoa! Heck yeah!
Yeah.
There we go.
We do not show up Stevie in this room.
Oh man.
This is a piece of garbage.
Thank you.